Hello, my name is Stryker Waddell. I'm a sophomore of electrical engineering here at the University of Arkansas. I'm also an intern for the National Center for Reliable Electric Power Transmission, or NCREPT, a University 6 MVA high-power testing facility. Today, I'll be presenting the Jacob's Ladder demo, which is part of the Wonders of Wattage outreach program. This outreach program was created by the U of A to share exciting and fun physics and engineering concepts in both fun and interactive ways. All the demos were built by students. The Jacob's Ladder is both visually exciting and scientifically important. It helps demonstrate electrical breakdown of air, arc flash behavior, and how transmissions work, all while reinforcing safety and inspiring curiosity. Let's start with the transformer. Inside every transformer, there are two coils of wire, a primary coil and a secondary coil. In this demo, the primary coil is connected to a standard 120 volt wall outlet. When current flows through the circuit, it creates an electromagnetic field. This field transfers energy to a secondary coil, which turns it back into electrical current, but at a different voltage. The change in voltage depends on the number of turns in each coil. If the secondary coil has more turns than the primary coil, the transformer steps up the voltage. If it has fewer turns than the primary coil, it steps down the voltage. In our case, the transformer takes 120 volts and steps it up to 15,000 volts. So it's a step-up transformer. Now that we have 15,000 volts coming out of the transformer, that voltage is applied across two rods, or these electrodes right here. When the voltage is high enough, it breaks down the air between the two electrodes and forms a conductive path. This is called an arc flash. The operation of the Jacob's Ladder is governed by Paschen's law, which describes the breakdown voltage needed to ionize a gas, in this case air, between two electrodes. According to Paschen's law, the breakdown voltage depends on the pressure of the gas, distance between the electrodes, and the composition of the gas. For atmospheric pressure, the breakdown field strength is about 3,000 volts per millimeter gap. In this demo, the transformer applies around 15,000 volts, which is enough to ionize the air between the rods and create a conductive plasma channel, or an arc. The electricity jumps across the gap, creating a visible arc that heats the air. The heated air around the spark becomes less dense and rises, pulling the spark upwards along the electrodes. Electricity always takes the path of least resistance. As the arc rises, the gap between the electrodes widens, increasing the resistance. Eventually, the arc becomes unstable and extinguishes. This process then restarts at the bottom, creating a cycle. This demo is a great way to visualize voltage, insulation, and thermal properties of air, as well as how electricity takes the path of least resistance, all in one exciting display. While this demo is safe under controlled conditions, the dangers of electricity and the dangers of arc flashes are very real, and can reflect what can happen in substations, transformers, or industrial power systems when faults occur. We hope this gave you a better appreciation for the power and danger of electricity and why engineering safety, design, and education are so important. Thank you for watching.